The night sky was once a chaotic tapestry of unknown lights. We will explore the early scientific instruments that transformed ancient observation into prediction, revealing how humanity first learned to read the future in the stars. By the end of this journey, you will understand how simple tools of brass and stone laid the foundation for our modern world. How did a device recovered from an ancient shipwreck predict eclipses for decades? And what secret knowledge allowed medieval scholars to hold the cosmos in the palm of their hand? What does our relentless drive to forecast tomorrow tell us about ourselves today? Recovered from the depths over a century ago, the Antikythera Mechanism was initially a lump of corroded bronze and wood, its secrets locked away. It took modern imaging technology to reveal the truth that this was an intricate astronomical calculator, a device of interlocking gears that could predict the future movements of the heavens. This was not a simple clockwork. Its gears, some with teeth cut with astonishing precision, modeled the complex dance of the moon, the sun, and the planets. It could show the phases of the moon, forecast eclipses, and even account for the subtle wobbles in the moon's orbit, a phenomenon we call lunar anomaly. To achieve this with hand-cut brass gears without any electricity or digital processing is a feat that stuns engineers even today. The very existence of this machine shatters our assumptions about ancient technology. It tells us that the drive to predict celestial events was so powerful that it fueled engineering innovation on a scale we scarcely imagined. This was not merely philosophical speculation. It was a physical, mechanical reality you could hold in your hands. So how did its creators acquire the knowledge to build such a device? The answer lies not in the machine itself, but in the centuries of patient sky watching that came before it. This patient observation was a legacy written in moonlight and shadows. For generations, priest astronomers across the ancient world became meticulous scribes of the sky. In Babylon, they pressed cuneiform symbols into clay tablets, recording the precise movements of planets. In China, imperial astronomers noted the sudden appearance of what they called guest stars, the comets and supernova that disrupted the celestial order. Their tools were simple, often just marked stones, sighting poles, or the grand alignments of monolithic structures like Stonehenge, which captured the sun's rays on a solstice with breathtaking accuracy. Their motivation was deeply practical, tied to the rhythms of planting and harvest, and to the sacred calendars that governed their societies. They were not just watching, they were searching for order in the apparent chaos. Over centuries, this relentless data collection revealed profound truths. They noticed, for instance, that a similar pattern of eclipses would repeat itself every 18 years and 11 days, a cycle we now call the Saros cycle. This was a monumental realization. The celestial events were not random acts of capricious gods, but followed predictable mathematical rhythms. This hard-won knowledge, this library of the sky built over lifetimes, was the essential raw material. But a new problem emerged. How could this generational wisdom, locked away in scrolls and memory, be made tangible? How could you hold this complex celestial clockwork in your hands? The answer would not be written on clay or parchment, but forged in metal and gear. This desire to hold the cosmos, to physically manipulate its cycles, found breathtaking expression in the Armillary Sphere. Picture a series of intricate metal rings, nested one within another, all revolving around a central sphere representing our Earth. This was not a mere ornament. It was a working model of the entire heavens, a cosmic skeleton forged in brass. Greek astronomers like Eratosthenes, the same man who calculated the Earth's circumference with stunning accuracy, pioneered these devices. Later, the great Claudius Ptolemy saw in the Armillary Sphere the perfect instrument to demonstrate his Earth-centered universe, a system of perfect circles governing the paths of the stars. Each polished ring had a precise purpose. One ring traced the celestial equator, another the path of the sun known as the ecliptic, and others marked the meridians arching across the sky. By carefully rotating these rings to match the night one had just observed, an astronomer could solve complex problems. They could predict when a specific constellation would rise above the horizon, or calculate the sun's position for any given day of the year. It made the abstract mathematical theory of a celestial sphere something a student could literally hold in their hands and turn. The elegant geometry of the cosmos was no longer just an idea, it was a tangible, mechanical reality. This device was a profound bridge, connecting the pure philosophy of a mathematically ordered universe with the practical need to forecast celestial events. But once you have a physical model of the heavens, a new and inevitable question arises. What if you could make it run on its own? What if you could build a machine that would not just model the sky, but automatically calculate its future? That leap from a stationary model to a self-calculating machine was revolutionary, but the next great innovation made the cosmos truly portable. The astrolabe was the medieval world's pocket computer, a disk of brass and engraved plates that held the entire sky in the palm of your hand. Its design was a masterpiece of mathematical translation, projecting the three-dimensional dome of the heavens onto a flat, two-dimensional surface. At its heart was a rotating star map, pierced with the most prominent constellations, overlaid on a plate etched with lines for altitude and direction. By suspending the device and aligning its sighting rule with a known star, a user could tell the time at night, calculate the sun's position before dawn, or determine their latitude. It transformed abstract celestial geometry into a series of practical, solvable problems. While its origins trace back to the Greek astronomer Hipparchus, it was Islamic scholars who refined the astrolabe into its most sophisticated form. They added intricate scales for calculating prayer times and for finding the Qibla, the direction toward Mecca, embedding their spiritual needs directly into this instrument of science. For centuries, this single device was the indispensable companion for astronomers, astrologers, and navigators alike. It compressed libraries of astronomical data into a portable, personal tool. This was knowledge you could carry in a pouch, taking the power of prediction out of the isolated library and directly into the field. The cosmos was no longer a distant mystery, but a practical guide for daily life and long journeys. This drive for portable, practical knowledge would soon push explorers to demand even more from their instruments, leading to a device that could conquer the greatest uncertainty of all, the open sea. Out on the open ocean, the familiar landmarks of the coast vanished, leaving only the vast, featureless expanse of water and sky. The sophisticated astrolabe, so brilliant on land, was nearly useless on a shifting deck. A new kind of instrument was needed, one built for the harsh reality of the sea. Enter the Mariners Astrolabe, a heavier, simplified brute of a tool. Cast from thick brass to resist the wind, its design was stripped of all ornamentation, a pragmatic device with one core function: to measure the sun's height at its daily peak. By knowing the sun's exact angle above the horizon at local noon, a navigator could calculate their latitude, their position north or south on the globe. It was a single, crucial data point in a world of utter uncertainty, but staring directly at the sun to take this measurement was both difficult and dangerous. The solution was elegantly simple. The cross staff, a basic wooden rod with a sliding crosspiece, allowed a sailor to measure the angle between the horizon and the sun without blinding himself. He would place the rod against his cheekbone, slide the crosspiece until its lower end touched the horizon and its upper end just touched the sun, then read the angle from a scale on the rod. Later, the backstaff refined this further, using the sun's shadow to allow the navigator to keep his back to the blinding light entirely. These tools transformed a terrifying gamble into a calculated endeavor. With the ability to reliably determine their latitude, sailors could venture across the Atlantic and around the Cape of Good Hope with a newfound confidence. They were no longer merely drifting, they were actively predicting their position on the planet's surface. This power to chart a course to new worlds and establish the first global trade routes proved the ultimate value of celestial prediction. It was no longer just about understanding the heavens, but about using that understanding to master the Earth itself. And as explorers mapped the globe, a new frontier for prediction emerged, one that required measuring time itself with unprecedented precision. But the open sea was not the only realm that demanded a new kind of measurement. To predict the heavens with true precision, you first needed to master a far more elusive dimension, time itself. The steady dripping of water and the silent fall of sand became the heartbeat of scientific progress. In ancient civilizations, from the courts of Egypt to the observatories of China, the clepsydra, or water clock, transformed time from a vague concept into a quantifiable resource. This was not a simple bucket. A clepsydra was an engineered system, often using multiple chambers to maintain a constant water pressure, ensuring the flow from one vessel to another was as regular as possible. This regulated trickle powered intricate astronomical models, timed the speeches of orators in Athenian courts, and introduced the revolutionary idea of a standardized, measurable duration that continued even through the night, independent of the sun. It moved timekeeping away from the cyclical, daylight-dependent nature of the sundial and toward a continuous, linear flow. This linear perspective was essential, for it allowed observers to record not just when a lunar eclipse began, but exactly how long it lasted, creating a data point that could be compared to eclipses from decades past. Alongside the water clock, the Sandglass offered a simpler, more robust solution for marking shorter intervals. Its consistent trickle of sand was crucial for navigation, timing the watches on a ship, and for early scientific experiments that required a known duration. By quantifying time into discrete, repeatable units, these humble devices created the very temporal framework upon which all predictive science is built. They allowed for the precise comparison of a past celestial event with a future prediction, turning observation into verifiable fact. This fundamental mastery of time's passage was the silent, necessary partner to every celestial instrument. It was the prerequisite for the next monumental challenge, one that had baffled astronomers for millennia, predicting the perplexing paths of the planets as they wandered through the stars. Yet the planets presented a stubborn challenge to any simple model of perfect circles. Their paths were not orderly, but looped and backtracked against the backdrop of stars in a perplexing dance. To tame this celestial chaos, Claudius Ptolemy devised a system of breathtaking geometric complexity in his great work, the Almagest. He placed a motionless Earth at the center of it all, but to account for the planet's strange reversals, he proposed that each world traveled on a small circle, called an epicycle, whose center itself traveled on a larger circle around the Earth, known as the deferent. It was a universe of wheels within wheels, a cosmic clockwork of interlocking circles. The brilliance of this system was not its physical truth, but its raw predictive power. By carefully adjusting the sizes and speeds of these invisible circles, Ptolemy's rules could forecast a planet's position with remarkable accuracy for its time. This mathematical model became the universal language of astronomy for over a millennium. But how did this complex geometry become useful to a ship's captain or a calendar maker? The answer lies in the astronomical tables derived from it. Teams of calculators would spend months, even years, applying Ptolemy's intricate rules to generate pages of numbers. The Alphonsine tables, commissioned by a king in the 13th century, were one such monumental effort. They listed the future positions of the sun, moon, and planets for decades to come. Think of these volumes as the preloaded software of the medieval world. An astrologer could look up the precise location of Mars on a specific future date to cast a horoscope. A navigator, though with less precision at sea, could gain a general sense of the heavens he would encounter. These tables turned an abstract philosophical model into actionable data that shaped decisions, from the timing of a coronation to the departure of a trading fleet. This entire enduring system teaches us a profound lesson about the nature of science itself. A model does not need to be fundamentally true to be incredibly useful. Ptolemy's Earth-centered universe was a fiction, a beautiful and complex lie, but it worked. It generated reliable predictions that ordered society and guided exploration for over 1,000 years. Its very success, however, created a tension that would simmer for centuries. The machinery had become so convoluted, with its many layered circles, that a lingering question began to grow in the minds of later thinkers. Could the cosmos, seemingly a creation of divine order, truly be so complicated? The desire for a simpler, more elegant truth was quietly gathering strength, waiting for a catalyst to ignite a revolution in human thought. While Europe grappled with its own complex challenges, a vibrant intellectual revolution was unfolding under the caliphates. The Islamic Golden Age became the new engine of astronomical progress, a period of breathtaking synthesis and innovation. Scholars across this vast realm saw the Greek inheritance not as dogma to be memorized, but as a foundation to be rigorously tested, corrected, and expanded. They established grand observatories like the one at Marrakech, which housed massive, newly invented instruments for measuring the stars with unprecedented precision. Astronomer al-Battani, working from his observatory in Syria, meticulously recalculated the solar year and the precession of the equinoxes, correcting figures that had been accepted since Ptolemy. His data was so accurate it was used for centuries, but the most brilliant leap forward was conceptual. Nasir al-Din al-Tusi, facing the same problem of planetary motion that had troubled the Greeks, devised an elegant geometric solution known as the Tusi couple. Imagine two circles, one rolling inside the other. This simple arrangement could generate a perfect back and forth line from nothing but circular motion. It was a mathematical insight that elegantly reproduced the looping paths of the planets without the need for Ptolemy's more cumbersome mechanisms. This was not just preservation, it was a fundamental creative advance. The results of this flourishing were compiled into comprehensive astronomical handbooks known as Zhang. These volumes were far more than star charts. They were detailed computational manuals filled with revised tables, new observational data, and instructions for using instruments. They became the essential reference works for anyone seeking to predict celestial events, from the timing of a new moon to the position of Mars. The legacy of this era is profound. It provided the very tools and the refined data that would later spark the European Renaissance. When thinkers like Copernicus began to question the ancient models, they were standing on the shoulders of Islamic scholars who had already perfected the art of observation and paved the way for the next great leap, a new instrument that would finally shatter the crystal spheres. A simple quarter circle marked with a scale became one of history's most transformative tools. This was the quadrant, a device whose elegant geometry could capture the angle of a star. Its origins were humble, rooted in the land surveyor's need to measure the height of a building or the slope of a hill. But in the hands of an astronomer, this same principle was turned toward the heavens. By sighting a star along the quadrant's straight edge and reading where a weighted plumb line crossed the graduated arc, one could determine its precise altitude above the horizon. This single number, the star's angular height, was a fundamental key. It unlocked the local time at night and provided a crucial check on the latitude found by other means. The quadrant made the sky measurable in a way that was both immediate and profoundly useful. Yet its true potential was realized when it was scaled up to monumental proportions. Fixed immovably to a north-south wall in a dedicated observatory, the mural quadrant became a permanent instrument of science. Its massive size, sometimes spanning several meters, allowed for a finely divided scale that could be read with astonishing accuracy. The Danish nobleman Tycho Brahe understood this power completely. At his island observatory of Uraniborg, he used giant mural quadrants to meticulously chart the positions of the planets night after night, year after year. His resulting star catalogue was the most precise the world had ever known, a data set so accurate it would later become the essential evidence for a new model of the solar system. The quadrant's design was equally powerful in its portable form. A navigator at sea or a surveyor in a distant land could carry a smaller version, often beautifully crafted from wood or brass. By combining a sighting rule with a hanging plumb bob, this handheld device brought laboratory-grade precision directly into the field. Its operation was a study in focused simplicity, a direct translation of celestial geometry into a number that could be logged and calculated. This cycle of improvement, where a better tool yields better data which then demands an even better tool, is the very engine of scientific progress. The quadrant perfected the art of measuring the visible sky. But what if you could see what was previously invisible? What if you could extend human vision beyond its natural limits to gather light from the faintest stars? This relentless drive for better data was about to be supercharged by an invention that would forever change our place in the cosmos. A simple tube with two pieces of glass shattered a 2,000-year-old truth. In the first decade of the 1600s, a new instrument from the Netherlands spread across Europe, and when Galileo Galilei pointed his improved version skyward, the universe was irrevocably changed. He saw not a perfect, smooth sphere, but a moon scarred with mountains and valleys, a world not unlike our own. He watched Venus exhibit a full set of phases, proving it orbited the Sun, not the Earth. Most stunningly, he discovered 4 small moons circling the planet Jupiter, a clear demonstration that not everything in the cosmos revolved around our own world. These were not merely distant points of light, they were dynamic physical bodies. The telescope transformed the heavens from a theoretical diagram of perfect circles into a messy physical reality. This new tool did not just magnify vision, it fundamentally altered the nature of evidence itself. For the first time, scientific truth was no longer determined solely by which mathematical model best fit centuries of naked-eye data. Now a person could see direct physical proof. The crystal spheres of Ptolemy's universe, a comforting idea of nested, transparent shells, could not survive the sight of Jupiter's own orbiting moons. The telescope provided the crucial, undeniable observations that forced the abandonment of an Earth-centered cosmos and gave the Copernican sun-centered model the weight of physical reality. This was the ultimate triumph of observation over pure reason. Astronomy was no longer just a branch of mathematics. It became an empirical science grounded in what could be seen, measured, and confirmed. The universe was suddenly larger, more complex, and far more knowable. With this explosive expansion of the visible cosmos, the old forms of prediction, built on an Earth-centered framework, became instantly obsolete. A new universe demanded a new physics and a new kind of prophecy. The steady swing of a pendulum finally tamed the unruly flow of time. Before its invention, even the best clocks could drift by minutes each day, a frustrating margin of error for anyone trying to pin down the precise movements of the cosmos. Then, in 1656, the Dutch scientist Christian Huygens transformed a simple observation into a revolution. He took the pendulum, whose regular beat Galileo had noted, and coupled it to an escapement mechanism, creating the first pendulum clock. Its impact was immediate and profound. The error in timekeeping shrank from minutes per day to mere seconds, a quantum leap in precision that reshaped the very fabric of scientific inquiry. This was not merely a better clock for the town square. It became a fundamental instrument for the laboratory and the observatory. Astronomers could now measure the exact moment a star passed behind a crosshair in their telescope, a measurement called a transit, with a reliability previously unimaginable. This new chronological certainty directly improved the determination of observers' longitude on Earth and forced a refinement of the entire celestial map. The pendulum clock provided the essential, reliable time base that all experimental science had been missing. Physicists could now investigate the natural world with a stopwatch in hand, so to speak. They could measure the acceleration of a rolling ball, the period of an oscillation, or the fall of an object with a consistency that made quantitative laws possible to discover. This precise measurement of short, consistent intervals was the crucial data that allowed thinkers like Isaac Newton to formulate his laws of motion and universal gravitation. The pendulum clock did more than tell time. It provided the immutable temporal grid upon which the new, mechanistic universe could be mapped. For the first time, the laws governing a falling apple and the orbit of the moon could be tested against the same unerring beat, linking the heavens and the earth with a newfound chronological certainty that would power the coming age of reason. As the telescope stretched our vision to the stars, a second instrument was turning it inward, toward a universe teeming with life on the very edge of sight. In the same era that Galileo was charting the moons of Jupiter, a Dutch draper named Antony van Leeuwenhoek was polishing tiny, powerful lenses. Through these handmade marvels, he saw a world no one had ever imagined. A single drop of pond water became a thriving ecosystem, filled with what he called animalcules, tiny creatures swimming and darting in a realm previously invisible. This was not a distant celestial reality, but a hidden world existing all around us and even within us. The microscope did more than just reveal new life, it revealed a new frontier for prediction itself. By meticulously observing these microorganisms, scientists could begin to trace the unseen threads of cause and effect that governed health and illness. They could observe the life cycles of microbes and start to understand how they spread, laying the groundwork for predicting and ultimately preventing outbreaks of disease. This was a profound shift. Prediction was no longer confined to the grand clockwork of the planets. It was now a tool for understanding the most intimate processes of life. The principles that guided an astronomer were precisely the same ones that guided a biologist: patient observation, meticulous recording of data, and the relentless search for repeating patterns. Whether the subject was the orbit of Mars or the division of a cell, the scientific method proved to be universally powerful. This parallel revolution underscored a monumental truth: that our instruments do not just answer old questions, they redefine the very boundaries of what we can ask. The drive to predict had successfully leaped from the scale of galaxies down to the scale of a single drop of water, proving that the universe was full of patterns waiting to be read, if only we had the tools to see them. That smartphone in your pocket carries the ghost of an astrolabe. Its precise orientation sensors and global positioning system are the direct descendants of those brass discs and magnetic needles, miniaturized and digitized into silicon. This is not a vague metaphor, but a direct technological lineage. Those early navigators straining to measure a star's angle were pioneering the very same principle your phone uses to know which way you are facing. Even more profoundly, the entire global positioning system is a constellation of flying clocks. Each satellite broadcasts an exquisitely precise time signal, and your device calculates its position on Earth by measuring the tiny delays in receiving those signals, a process that is the ultimate evolution of celestial navigation. We have simply swapped the stars for satellites and the quadrant for a quantum-accurate atomic clock. This same predictive drive shapes our daily weather forecasts. While they are generated by supercomputers solving equations of unimaginable complexity, the foundational data they consume still comes from instruments measuring atmospheric pressure, temperature, and wind speed. These are the same fundamental variables that early scientists first learned to quantify with their simple barometers and anemometers. The tools have changed beyond recognition, but the core scientific principle is identical. We use instruments to gather data, we search for patterns within that data, and we build models to predict a future state. Understanding this deep lineage does more than satisfy historical curiosity. It connects us to the long, unbroken arc of human ingenuity, highlighting our enduring drive to not just live in our environment, but to comprehend it, to anticipate its changes, and to navigate it with confidence. This historical perspective transforms the sophisticated tools we take for granted from mere consumer products into the latest chapter in an epic story of discovery. Power to read the heavens was once the ultimate political currency. To predict an eclipse was to demonstrate a direct line to the cosmos, a claim that could legitimize a ruler or destabilize a dynasty. In ancient China, the emperor's court astronomers held a position of terrifying responsibility. Their role was to maintain harmony between the celestial and terrestrial realms, and a failure to forecast a solar eclipse was interpreted as a catastrophic break in that harmony. It was seen as a failure to understand the mandate of heaven itself, and such an error could result in severe punishment for the astronomer. The stakes of prediction were not merely academic, they were a matter of life and death, cementing the authority of the state through its exclusive command of celestial knowledge. Across the world in Europe, a different kind of revolution was unfolding through the printed page. The annual almanac, a cheap and wildly popular publication, brought predictive power directly into the homes of common people. These pocket-sized books contain tide tables, weather forecasts, and the dates of future eclipses, blending astronomy with astrology and practical advice. For a farmer, knowing the best time to plant crops based on the moon's phase was invaluable. For a merchant, understanding the coming seasons was crucial for planning trade. This mass production of predictive knowledge began a slow but irreversible shift. Authority was no longer solely vested in a king who claimed a divine connection or a church that interpreted God's will. It was increasingly found in the reproducible, testable data printed in a book that anyone could buy. The instruments of prediction, from the observatory's quadrant to the printer's press, became levers of profound social change. They did not just chart the movements of planets, they challenged the very structure of society by empowering individuals with knowledge that was once the exclusive domain of the elite. This transformation redefined humanity's relationship with authority, setting the stage for a world where truth would be sought not in decree but in evidence. The true revolution in celestial prediction was written not in brass but in symbols. Long before the first gear was cut for an astronomical machine, the ancient Greeks had forged a new language for describing the cosmos, geometry. This was not merely the study of shapes, it was a logical system for modeling reality itself. The perfect circle became the idealized path of a planet, and the angles inscribed within it could be used to calculate distances otherwise impossible to measure. This geometric language provided the first rigorous framework for turning observations into a coherent model, a set of rules that the heavens seemed to obey. Yet geometry, for all its power, was primarily a language of description. It could map the what and the where, but it struggled with change and motion over time. A new mathematical tool was needed to capture the dynamics of the universe, a system for handling the unknown. That tool was algebra, a word of Arabic origin that means the reunion of broken parts. Developed and refined by scholars in the Islamic world, algebra introduced the power of abstraction. It used symbols to represent variables and unknowns, creating a flexible toolkit for solving problems of all kinds. An astronomer could now write an equation to represent the relationship between a planet's speed and its distance, and then solve for the future position. This was a monumental shift from describing a static cosmos to calculating its future state. The ultimate mathematical instrument for handling continuous change arrived with calculus, independently developed by Isaac Newton and Gottfried Wilhelm Leibniz. Calculus provided the means to analyze anything in flux, from the accelerating speed of a falling apple to the subtly changing orbital velocity of the moon. It was the key that unlocked the physics of motion. Johannes Kepler's story perfectly illustrates this evolution. He spent years drowning in the mountains of precise planetary data compiled by Tycho Brahe. Geometry alone could not make sense of the orbits, but through relentless mathematical analysis, Kepler discovered that the planets moved in ellipses, not perfect circles. He had used mathematics as a filter, sifting through raw data to extract a fundamental truth that the naked eye could never see. His 3 laws of planetary motion were pure mathematical prophecy. Then came Newton, who wielded the new tool of calculus to show that the very same mathematical force that pulled an apple to the ground also kept the moon in its orbit around the Earth. This was the ultimate unification, all achieved through the abstract power of equations. Without this invisible instrument of mathematics, the meticulous data from quadrants and telescopes would have remained a collection of curious facts like unconnected dots on a page. Mathematics provided the lines to connect them, revealing the hidden picture of a predictable cosmos. It is the silent engine in every instrument, the universal translator that turns the whisper of observation into the clear voice of forecast. The Earth itself held secrets that ancient inventors were determined to hear. While astronomers charted the predictable heavens, the ground beneath their feet remained an unpredictable and terrifying force. In 2nd century China, the brilliant scholar Zhang Heng confronted this chaos with a masterpiece of engineering, the Seismoscope. This ornate bronze vessel stood as a silent sentinel, its surface ringed with dragon heads, each clutching a bronze ball above the open mouth of a corresponding frog. Its beauty, however, concealed a brilliant mechanical insight. Inside, a cleverly suspended pendulum was connected to a set of levers. When seismic waves from a distant earthquake reached the device, the pendulum would swing, tripping a single lever that released a ball from just one dragon. The clang of that ball landing in the frog's mouth did more than signal a tremor. It pointed the way. It announced the direction from which the earthquake had come, often for a quake so distant that no local shaking had been felt at all. This was not prediction, but it was the essential foundation for it: rapid detection and location. It transformed an invisible, mysterious event into a tangible, localized fact. The seismoscope proved that the same principles used to model the cosmos, the translation of unseen forces into observable mechanical results could be applied to the very planet we stand on. It was an attempt to give the Earth a voice. This early foray into listening to our planet's deep movements established a new scientific frontier, one that would eventually evolve into the modern science of seismology and fuel our enduring, vital quest to one day foresee the Earth's tremors before they begin. A simple rooster turning on a church spire was one of humanity's first dialogues with the invisible force of the atmosphere. The wind vane, tracing its lineage back to the elegant Tower of the Winds in ancient Athens, gave a name and a direction to the unseen. It transformed the wind from a mere feeling on the skin into a quantifiable fact, pointing north, east, south, or west. This was the most fundamental variable in the weather's complex equation, telling a farmer which way a storm might arrive or a sailor how to set his sails for the fastest passage home. But direction was only half the story. How could one measure the wind's strength, its true power? Renaissance thinkers answered with the first anemometers, simple devices like a flat plate that would be pushed backward by the gusts. The further the plate swung, the faster the wind was blowing. It was a crude but effective start, a way to assign a number to the air's relentless push. These were not predictive tools in themselves. They offered only a snapshot of the present moment. Their true genius was revealed over time, when a curious individual began to diligently log the wind's direction and force day after day, season after season. Something remarkable happened. Patterns began to emerge from the pages of a notebook. A shift to the northeast might consistently bring colder air, while strong southern winds often preceded a period of rain. This patient, systematic recording was the quiet birth of empirical meteorology. It moved weather prediction out of the realm of folklore and proverbs and into the world of data. The whims of the sky were slowly giving up their secrets, not to magic, but to the meticulous discipline of measurement. These humble instruments began the long process of translating the chaotic symphony of the atmosphere into a language of numbers that could one day be understood. The darkness of the open sea offered its own kind of clock. Without a pocket watch or a visible sun, sailors turned to a simple, elegant tool carved from wood or brass, the Nocturnal. Its design was a study in focused brilliance, a direct answer to the most basic human question in the dead of night: what time is it? By holding the device up and sighting the North Star through its central hole, a user would then rotate an arm until it precisely lined up with the two pointer stars of the Big Dipper, those familiar guardians of the northern sky. Where the arm then fell on the outer scale revealed the hour. This single, deliberate action transformed the slow, majestic wheel of the stars into a readable dial. The entire principle relied on sidereal time, the subtle fact that the stars returned to the same position in the sky about 4 minutes earlier each night, a rhythm completely separate from our solar day. The Nocturnal took this complex celestial clockwork and compressed it into a single, silent measurement. It was a specialized offshoot of the mighty Astrolabe, stripped down for one essential nightly task. In the southern hemisphere, where the North Star vanishes below the horizon, navigators performed the same ritual using the brilliant Southern Cross, proving the universal human need to mark time by any fixed point in the heavens. This humble instrument did not just tell time, it represented the ultimate democratization of celestial knowledge. You did not need to be a scholar who understood the mathematics of the spheres. You simply needed to know how to hold the device and align its pointers. The profound, generational understanding of the star's apparent motion was encoded directly into its calibrated disk. With a turn of the wrist, the vast, impersonal cosmos became a personal timepiece, a constant companion in the wilderness or on the waves. It was the final, beautiful proof that the ultimate purpose of these early instruments was not to complicate the heavens, but to simplify them. to place their predictive power directly into the hands of anyone who dared to look up and learn its language. A darkened room could hold a perfect, living image of the world outside. This was the magic of the Camera Obscura, a simple device that revealed the fundamental laws of light. By allowing sunlight to enter through nothing more than a tiny pinhole in one wall, it projected an upside-down scene of the bustling street or the tranquil landscape onto the opposite wall. The effect was mesmerizing, a silent, moving painting created by nature itself. For centuries, this phenomenon was a curiosity, but in the hands of Renaissance masters, it became a profound scientific tool. Leonardo da Vinci studied its principles to decode the mysteries of linear perspective, understanding how the eye perceives depth and distance. The astronomer Johannes Kepler took this further, using a portable tent camera obscura to meticulously study the formation of images, laying the groundwork for the science of optics. The camera obscura demonstrated a revolutionary truth that light travels in perfectly straight lines. This single principle is the silent, invisible architecture upon which all lens-based instruments are built. The telescope that Galileo pointed at the moons of Jupiter, the microscope that revealed a hidden universe in a drop of water, both rely on this foundational understanding of how light behaves and can be bent and focused. The camera obscura did not predict an eclipse or measure a star's angle, but it did something just as vital. It gave us mastery over the very medium of observation. It expanded the canvas of science from what we could see with our naked eye to what we could project, manipulate, and ultimately understand. This humble device proved that before we could accurately predict the cosmos, we first had to learn how to see it. A king's forearm could not be the foundation for science. The ancient Egyptian cubit, the length from a pharaoh's elbow to the tip of his middle finger, was a brilliant solution for building pyramids, but it was inherently personal and local. What if the next pharaoh had a different arm length? The entire system of measurement would shift. This was the fundamental problem that plagued early science, a chaotic landscape of incompatible units where one person's inch was another person's thumb width, and one city's pound was another's stone weight. Without a shared language of measurement, the data collected by an astronomer in Cairo was utterly useless to a colleague in Cordoba. Prediction, which relies on the precise comparison of past and future observations, was impossible. The quiet, unheralded revolution was the creation of universal standards. This was not about building a better telescope, but about ensuring that every observer using that telescope was speaking the same numerical language. The French Revolution, in its drive to reinvent society, gave the world one of its most enduring gifts, the meter. It was defined as 1/10,000,000th of the distance from the North Pole to the equator, a breathtakingly ambitious attempt to anchor measurement not in a human body, but in the planet itself. Suddenly, a length was no longer arbitrary. It was a fraction of the Earth's very circumference. This push for standardization extended to every tool in the scientist's kit. The precise division of a circle into 360 universal degrees meant that an angle measured with a quadrant in Tycho Brahe's Danish observatory could be directly plugged into the calculations of Johannes Kepler in Prague. The meticulous calibration of weights and scales ensured that an experiment on gravity in England could be exactly replicated in Italy. This was the birth of truly collaborative science. It transformed individual genius into a cumulative global enterprise. The ability to compare, to verify, and to build upon the work of others is the engine of scientific progress. That engine would have stalled forever without the silent, painstaking work of standardization, the unglamorous agreement on a common ruler that allowed humanity to finally measure the universe with one voice. Even the most perfect model of circular orbits could not explain the sudden, brilliant visitor in the night sky. In 1572, a new star appeared in the constellation Cassiopeia, shining so brightly it was visible even during the day. This was a supernova, a stellar explosion that defied the ancient doctrine of an unchanging celestial realm. Tycho Brahe meticulously measured its position, proving it lay far beyond the Moon, in a region supposedly immutable. His data was impeccable, but his instruments and the models they served had no capacity to predict such an event. They were designed to track the known, cyclical motions of established bodies, not to forecast the birth of new ones or the appearance of unexpected comets that followed no schedule. The very philosophy of a perfect, clockwork universe built on circles created its own persistent blind spots. To account for the planet's stubborn refusal to follow perfect circular paths, astronomers were forced to add layer upon layer of geometric correction, those intricate epicycles that made the celestial machinery increasingly complex and unwieldy. The problem was not just in the theory, but in the physical tools themselves. A brass astrolabe, no matter how beautifully engraved, could warp with changes in temperature. A wooden quadrant could subtly bend over time, introducing tiny but cumulative errors into a lifetime of star positions. The finest craftsman's hand could not cut a gear tooth with the microscopic precision of a modern machine. These were not failures of intellect, but the honest boundaries of their era's technology. Yet these limitations were the very engine of scientific progress. The growing frustration with the inaccuracies of the Ptolemaic system and the nagging imperfections in the data created an intellectual tension that demanded resolution. Why did the models, for all their complexity, still not quite match the observed heavens? This was the puzzle that consumed Kepler, driving him to abandon 2,000 years of circular dogma and discover the true elliptical shape of planetary orbits. It was the gap between prediction and observation that gave Newton the critical evidence he needed to formulate his law of universal gravitation. The frontier of ignorance, so clearly mapped by what these instruments could not do, became the most fertile ground for the next great leap in human understanding. A brilliant design was useless if it remained locked in a single mind. The survival and evolution of these instruments depended entirely on a fragile, sprawling network for sharing knowledge. For centuries, the flickering lamplight of monastic scriptoria was one of the few beacons keeping ancient wisdom from vanishing entirely. Scribes, working with painstaking care, copied Greek and Arabic astronomical texts word for word, line by line, preserving the geometry of Euclid and the star catalogues of Ptolemy through Europe's most challenging eras. This handwritten tradition was a lifeline, but it was slow and vulnerable. Then, in the mid-15th century, the printing press introduced a new kind of power, the power of mass production for ideas. Suddenly, an intricate design for an astrolabe or a set of planetary tables could be printed not once but hundreds of times and sent across continents. Errors were no longer amplified with each new copy. Consistency became possible, and a scholar in Krakow could be working from the exact same diagram as a craftsman in Nuremberg. This was the infrastructure that allowed innovation to accelerate. Yet a printed page was still just a promise. To become a working instrument, that design needed the hand of a master artisan. In specialized workshops, these unsung heroes of science turned abstract lines on paper into polished brass and precisely divided scales. They were a unique blend of artist, engineer, and scientist, often working side by side with the scholars who drafted the designs, solving practical problems of weight, balance, and material in real time. This created a powerful feedback loop. The scholar provided the theory, the artisan built the physical object, and the user, whether a navigator or an astronomer, would report back on its performance, suggesting improvements for the next iteration. The global journey of the astrolabe perfectly embodies this process. A design refined in the Islamic world would travel to Spain, be translated, adapted by a local craftsman for a different latitude, and then find its way to a Parisian workshop where another improvement was made. Each culture, each artisan, added a layer of refinement. This was not a single story of invention, but a chorus of collaboration across time and space. It reminds us that our greatest tools are never truly finished. They are simply the latest version in a conversation that has been ongoing for millennia. The power to predict an eclipse stripped it of its supernatural terror. A celestial event that once signaled the displeasure of the gods, a reason for kings to tremble and for priests to offer sacrifices, was now revealed to be a simple matter of geometry and shadow. This was the quietest yet most profound revolution. The steady turning of a geared mechanism did more than calculate a future date. It fundamentally rewrote humanity's relationship with the cosmos. The universe was no longer a stage for divine drama, but a vast, intricate machine operating by a consistent and accessible set of rules. This demystification was the essential precondition for all modern science. If the heavens, in all their majesty, obeyed knowable laws, then why not the fall of an apple, the flow of blood, or the growth of a plant? The success of these instruments bred a new and powerful confidence, a belief that every aspect of the natural world was not a mystery to be feared, but a puzzle to be solved. This intellectual shift created an environment where figures like Newton and Galileo could thrive, not as heretics, but as explorers in a universe that was finally revealing its logical foundations. The true legacy of the Antikythera Mechanism and the astrolabe is not found in a museum display case, but in the very mindset of inquiry they helped to foster. They taught us to trust the evidence of a calibrated scale over the whisper of an omen, transforming our species from fearful observers of a chaotic world into confident seekers of a predictable order. Long before gears and brass, humanity's first astronomical computers were carved from the living earth. These megalithic structures were not built for shelter, but for sight. At a place like Newgrange in Ireland, a massive 5,000-year-old stone mound contains a narrow passage that aligns perfectly with the winter solstice sunrise. For just a few precious minutes on the shortest day of the year, a single blade of sunlight pierces the inner darkness, illuminating a sacred chamber. This was not a random act of construction, but a precise, deliberate engineering feat designed to capture a fleeting moment of celestial light, year after year. It was a promise written in stone that the sun would return and the days would grow long again. Across the ocean in the coastal desert of Peru, the 13 towers of Chanquillo form an artificial horizon on a hilltop. From specific observation points, this stone string of peaks functions as a massive solar calendar. As the sun travels its yearly path, it rises and sets in perfect alignment with a different tower, marking the date with a precision that could guide an entire society's planting and harvest cycles. These monuments were the ultimate communal project, demanding generations of labor and a shared vision of time itself. They required no moving parts because their mechanism was the planet's own rotation. Their gears were the sun and stars, and their clock face was the entire horizon. This was science on a truly monumental scale, an intimate collaboration between human ambition and the cosmic order. It proves that our ancestors were not just observers of the sky, they were architects of it, reshaping their world to hold a conversation with the heavens. From a silent stone chamber awaiting the solstice sunrise to the whirring gears of a brass calculator, these instruments share a common purpose. They are the physical embodiment of a profound human desire to reach beyond the present moment and grasp the future. This was never a journey about mere gadgets. It was a philosophical uprising, a slow and steady shift from a universe filled with capricious spirits to a cosmos governed by consistent, knowable laws. The ability to predict an eclipse with a machine, rather than pleading with a deity, fundamentally rewrote our role from fearful subjects to active participants in a knowable universe. That same intellectual courage born from these early tools now guides our most advanced explorations. The particle accelerators searching for the fundamental building blocks of matter and the space telescopes mapping distant exoplanets are the direct descendants of the Quadrant and the Astrolabe. They are all extensions of the same question first asked by an astronomer watching a shadow cross the moon. Our modern world, with its instant weather alerts and global positioning, rests upon this ancient foundation. Every time your smartphone pinpoints your location or a satellite image shows a storm forming, you are witnessing the living legacy of that first predictive spark. The story of these instruments is not a closed chapter in a history book. It is an ongoing narrative of curiosity and ingenuity, a testament to our unbroken drive to look at the stars, to measure the wind, and to ask with ever more powerful tools what happens next.